session, that is tutorial 5, and we are going 15 minutes late. Not a issue, big issue. So we are going to start this session with me, uh, Dr. Saurabh Deroy, with us, our former postdoctoral research associate of Computer Vision Lab, with me today, and I am very happy that Saurabh is with me, and he will demonstrate the using accessible and free dataset, each normal and abnormal with MATLAB, and basic performance analysis as a tutorial. So we are going to start. Saurabh, am I audible?
Yes, sir.
Okay, so we are going to start. This is the, as you know, that the biological cell imaging for diagnosis and early prediction of the cancer. Anyone, am I audible? Anyone from the participant, please?
Yes, sir.
Yes, sir.
And okay, thank you, Ronit. Okay, so then before starting this part, I will totally uh, giving the charge for the assistantship of this hands-on to Saurabh, and I think
Yes, sir.
Dr. Saurabh will beautifully present, and and if you any question and any other issues of the, that is the performance evolution, confusion matrix, ROC curve, and implementation of code demonstration. So I will request Saurabh, please start and give them the total demonstration as a presentation. Thank you. Please start, Saurabh.
Thank you. Okay, good evening, everyone. Myself, Saurabh Deroy, and I am the former Research Associate of Computer Science and Engineering Department at University. And today I am here to give a tutorial session on using accessible and free databases, each normal and abnormal, from the pap smear images, that is cytological images, with MATLAB and their basic performance analysis related to the computer vision problems. These are my outlines. First of all, I will give a brief introduction on the medical microscopic imaging and its various vision-based problems, what we deal in today's world. Then the data preparation for classification algorithm. Then the performance evaluation matrix, the confusion matrix, the performance evaluation matrix for the classification, ROC curve, implementation code demonstration, then the performance evaluation of the segmentation algorithms. Then based on the segmentation algorithms, we will also discuss about the intensity-based similarity measurement of the segmentation, performance evaluation matrix for segmentation validation, and the implementation code demonstration. So rather than describing a much about the medical microscopic imaging, I will give a brief introduction on what is actually it doesn't, what actually it does means. So medical microscopic imaging basically plays a vital role in cancer research and diagnosis. It enables the visualization of the cells, tissues, and subcellular structures at high resolution to detect or extract the morphological characteristics of the cells associated with the cancer. So these images basically help the pathologist or medical experts to identify the malignant transformation, that is the study of the tumor microenvironments, and evaluate their treatment response based on the drugs. So what we as a researcher do? Basically, we as a researcher contribute in three major domains related to the medical microscopic imaging. That is the medical microscopic image segmentation, then is classification, and is detection. Let's just understand what each of these terms actually means. So first of all, as Shashwat have already discussed, that medical microscopic image segmentation is basically deals with the extracting the shape and boundary of any organ, tissue, or lesion. So what it does, it basically classifies each pixel of the microscopic imaging, that is, it produces a marks showing which pixel belong to which structure. Means suppose in case of the pap smear image, if we have region of interest as the nucleus region. So basically, what after applying the segmentation algorithm, it will do what it will do. It will plot one pixels to the white pixels to the nucleus region, and rest of the pixels will be assigned as background, that is black pixels. So what we actually do, example, pap smear cytological image, if we give as an input, so it gives output as a pixel-wise marks separating nucleus region from the holistic microscopic imaging. So some of the common techniques are UNet, SegNet, and deep lab. Next comes the medical microscopic image classification. So the main goal of this classification is to identify what type of abnormality is present. Then it assigns a class level to the entire image. So basically the model looks into the holistic microscopic image and it predicts a class level. For example, in case of the binary classification, it gives whether the cell image is normal or abnormal. And if it is a multi-class classification, so it basically gives whether it is normal, mild, moderate, or severe. So the example is if it is input pap smear cytological images. So for binary classification, it will give normal or abnormal, and in case of the multi-class, it will give normal, mild, moderate, or severe. Some of the common techniques are sequential CNS or vision transformers, which are using nowadays. Next is the medical microscopic image detection. So it is basically similar to the classification and the segmentation task, but it basically locates where a specific object or abnormality is within the image, and it gives the class of this abnormality. So if we see the figure 3, then we can see that the nucleus region enlarges and it represents as an abnormal cell. And if the nucleus region is small, it gives a bounding box surrounding the nucleus region and it gives a class level that it is a normal. So what it does basically, it is an example that input is the pap smear cytological images, and output will be the bounding box surrounding the suspicious nucleus region. So it both classifies and localize each of the abnormal regions. Some of the common techniques are cluster RCNN, yellow, retina net, and detection transformers. So what we do, basically we have learned about various classification algorithms, segmentation algorithms. So how we will measure the performance of these classification algorithms. So one of the major tasks is to data preparation for classification algorithms. Suppose if we have the whole data set, what we have to do, we have to first divide the data set into training set and the testing set. The testing set is kept totally unknown from the training part. And in the training set, we further divide the training set into training set and validation set. Then on the training set, we basically run any of the machine learning algorithm, whether it is a classification, segmentation, or detection. And we basically, based on the machine learning algorithm, a model is developed, which is known as the predictive model. So we basically perform the, whether how the model will perform on the validation set, which is from the training set. So we basically measure the predictive performance of the model. So after the model is completely built, we generally perform the measure on the completely unknown set, which is known as the test set. So whatever we do with the training and validation set, it is known as the validation, and whatever we do with the testing set after final build of the model, it is known as the performance evaluation. So basically, the standard method is to divide the whole data set into 4:1 ratio, that 80:20 ratio, and after that, the training set is further divided into 60:20 ratio for performance evaluation. So next is the performance evaluation of the classification algorithms. We also called it as a classification evaluation matrix. So in case of the classification task, performance evaluation is one of the major steps to check how well our algorithm is performing on a test data. So before dividing into the evaluation matrix for classification, it is important to understand what is actually the confusion matrix. So what is actually this confusion matrix means, and how we calculate the performance based on this confusion matrix. Suppose, for example, if we consider that we have extracted certain features, that is mean, variance, standard deviations, skewness, kurtosis from each of the segmented nucleus region, and we assign certain class levels. Suppose if in case of class level 0, it means it is a normal class, and in case of the class level 1, it is predicting that it is a abnormal class. It is abnormal class. So here the what is given in the label is actually the ground truth levels. Then after applying the classification algorithm, we get certain levels, which we call it as a machine predicted levels. It also gives the output as a 1 and 0. So based on these two results, that is ground truth level and the machine predicted level, we calculate the confusion matrix, and the performance evaluation is done from the confusion matrix. So what is actually a confusion matrix? So confusion matrix is nothing but is a technique for summarizing the performance of a classification algorithm. So it basically depends on the four basic parameters, that is true positive, true negative, false positive, and false negative. Here, if we see the figure 7, actual values means the ground truth levels and the predicted values means the what machine is giving. Suppose if the actual level is 1 and the machine is also predicting it as a 1, then we called it as a true positive. Suppose the if it is actually negative, means it is a normal class, but the machine is predicting it as a cancer class, so it will be as a false positive. And suppose if it is a cancer class and machine is detecting as a non-cancerous, then it is false negative. And the vice versa is if it is a negative class, that is abnormal, and machine is also predicting it as an abnormal, then we called it as a true negative. So the basic target is to make the principal diagonal element as a high and off diagonal element always must be low to represent the model as a good perform model. So basically what we do, there are basically five major performance evaluation metrics, that is accuracy, recall, precision, specificity, and F1 score. A very important point to note that any single metric is not suitable for all the machine learning models and tasks. Metrics are chosen based on the problem that we are trying to solve. So what is accuracy? So accuracy is basically the ratio of the correctly classified points to the total number of points in the data set. We can convert it into percentage by multiplying by 100. So accuracy is basically the sum of the true positive plus true negative divided by sum of true positive plus true negative plus false positive plus false negative. But in case accuracy is also a good measure when the target variables in the dataset are nearly balanced. It will always give a good result when the dataset is balanced for both the classes. But accuracy should never be used as a measure when the target variable class is to bias towards certain class. Because if there is normal and abnormal class, if certain samples belong, most of the samples belongs to the abnormal class, so we cannot use this as a basic performance evaluation matrix. Here is one of the example. Suppose in our cancer detection with 100 people, only 5 people have actually the cancer. So let us assume that model is very bad and it predicts every cancer as a no cancer. So in doing so, it has classified those 95 cancer patients correctly, but in the meantime, it has also detected 5 cancer patients as non-cancerous. So now, even though the model is terrible at predicting the cancer, the accuracy is always 95%, which is not actually true. So therefore, accuracy is also not a good measure in all the cases. The next one is the recall. So recall is also known as the true positive rate. So it basically calculates the ratio of the positive points that are correctly detected by our model. So the basic formula is true positive divided by true positive plus false negative. And next one is the precision. And the precision basically predicts the accuracy of the positive prediction only. So therefore, in case of the precision, there will be true positive divided by true positive plus false positive. So let us consider an example. Similar problem in our cancer classification with 100 people, 5 people actually have the cancer. So let's say the model predicts every case as a cancer. So since we are predicting everyone as having cancer, our denominator, that is true positive and false positive, is 100, and the numerator person having the cancer and the model predicting his case as cancer is 5. So in case of this, we can find that the precision of such model is only 5%. Although accuracy is 95%, but we can see the precision is a good measure where it can detect the model have only 5% precision value. Next is the specificity. So specificity is a measure that tells us the ratio of the negative points that are correctly detected by our model. So in case of the precision, we have seen that the numerator is true positive. So in case of the specificity, the numerator is true negative and the denominator is true negative plus false positive. Next is the F1 score. So F1 score is basically the harmonic mean of precision and recall. It gives the balanced distribution between the recall and the precision. So the basic formula is F1 equal to 2 into recall into precision divided by recall plus precision. Next is the most important thing for visualization of the classification performance. We basically plot the ROC curve, that is the receiver operating characteristics curve. It is nothing but the plotting the graph between the true positive rate and the false positive rate. In the x-axis there will be the false positive rate, and in the y-axis there will be the true positive rate. So So true positive rate is basically TP, that is true positive divided by true positive plus false negative, and false positive rate is basically false positive divided by true negative plus false positive. Suppose, for example, we have two classes are well separated. We have considered that the classification model have two classes, and the model performs so well that the two classes are well separated. So we can see that the ROC curve reaches quickly to the one, and the area under curve is so good that it has the one value. So we can, if the ROC curve look like this, then we can say the model have good performance. And in case of the figure 9, we can see that ROC curve, some of the false negative and false positive are overlapping between the true positive and true negative. So ROC curve is reaching towards the one slowly. And the area under curve we have received as 0.7. So if such kind of curve happens, then we can say the model have only 0.7% accuracy. And in here also figure 10, if we see that the model have only 50% accuracy, then ROC curve will look like a linear curve. It will be a straight line from the center 0 towards the 1. And if the model is performing so much bad, then the ROC curve will never reach towards 1. It will go slowly from 0 to 1 towards the x-axis, and it will reach at the infinite time to the 1 towards the y-axis. So let us consider a numerical example of a binary classification problem of cancer prediction. In this case, false negative, that is person has cancer but the model predicted not having cancer, is a very important metric rather than false positive. So suppose there are total population of 1,000 peoples, and suppose there is one confusion matrix, that is if the cancer is negative and the model is also predicting it as cancer negative, so we can call it as a true negative. That is, from the 1,000 population, it has been model have predicted that 850 values are true negatives, and if there is cancer positive and the model is giving the cancer negative, so it is called as a false negative, where it is given as a 6. And the next one is the if the cancer is negative and the model is giving the cancer positive, so the false positive rate is 50. And if the cancer is positive and the model is also calculating that the cancer is positive, then you can call this as a true positive, and it have 94. So based on this confusion matrix, we generally calculate the definition of the number of positives, number of negatives, true positive, false negative, true negative, and the false positive. And based on this four evaluation matrix, that is from the confusion matrix, that is true positive, false negative, true negative, and false positive, we can calculate the accuracy, precision, recall, F1 score, and specificity of the model. So let us solve this problem. So suppose in this example, we have taken a random sample of 500 people, and there are teenage patients. Of these teenagers, 50 are actually diabetic. So the classification model basically predicted 100 total diabetic teenagers, and 45 of which are actually diabetic. So can we compute the recall and precision of the model from the confusion matrix? Yes, we can calculate. So from the given data, we can see that total number of samples are 500. And according to the question, the actual diabetic patients are 50 and predicted diabetics are 100. Therefore, the true positives means actually how much is the actual diabetic, that is 50. So among these two positive is 45. So from the two positive, we can calculate the false positive, that is 100 minus 45, that is 55 is the false positive, and false negative is 50 minus 45, that is 5, and true negative is 500, that is 500 number of population, so 500 minus 45 plus 55 plus 5, that is 395. So based on this, we can see the recall have 90% accuracy and the precision have 45% accuracy. So let us see the code. How can we can implement this code? So as it is a section of MATLAB, so I want to explain you about the MATLAB. That MATLAB is also a tool like a Python where we can develop various machine learning algorithms. So suppose let us consider that we have the actual levels, that is the ground truth levels of total 30 samples, among which the first 15 samples have normal class and the rest of the 15 samples have abnormal class, that is represented by class level 1. And the predicted, as I have said, it is a machine given output. So here we can see that the model have performed very well, due to which the predicted level is also similar to the actual level. So for this, first in the third line we have to calculate the column matrix of the actual and both the predicted. And we have to, in the next line, we have to see idx equal to, in the bracket, actual equal to 1. That means it basically stores the index of the actual values having value as a 1. Next, we have to calculate the number of positives and number of negatives. Positives is basically the length of the actual idx, means how much there is 1, and the negative are the how much there is labels with 0, and the total number of samples are p plus n, means here p comes 15 and n comes 15, so n equal to 30. So next we have to calculate the four matrix, that is true positive, true negative, false positive, and false negative. So based on the true positive and true negative, we basically calculate the false positive and false negative, where false positive is calculated as n minus tn, means from the total number of negative samples, whether it is two negatives, we can minus the true negative, that is from the total number of negative samples we subtract the true negative. And in case of the false negative, what we do, it is total from the total number of total number of positive samples, we subtract the true positives. Next we calculate the true positive rate, that is tp by p, and true negative rate, and I have already explained the formulas, that is true negative by n. So based on this performance evaluation matrix, we can calculate the accuracy, specificity, sensitivity, precision, recall, and F1 measures. And in the evaluate, we keep all the performance evaluation matrix, and as it is giving the performance evaluation matrix as point values, so basically multiply with 100, and we can get the result in the percentage value. So as we have seen that actual and predicting are matching completely, that is model which have actually the ground truth levels are 0, so the model is also predicting this class level as 0, and if the ground truth is having 1, then the model is predicting as the class level 1. So it is giving the 100% for all the performance evaluation matrix. So the next one is the performance evaluation of the segmentation algorithms. So appropriate choice of segmentation method for ascertaining the accurate shape of a suspicious region of an interest representing the abnormality is a crucial task. So none of the existing segmentation algorithms are applicable to all the images, and different algorithms are not equally suitable for a particular application. So however, a limited number of performance measures are not adequate to describe the efficiency of any segmentation algorithm. So one of the most important segmentation performance evaluation metrics is the intensity-based similarity measurement of segmentation, that is calculated from the binary marks of the ground truth and the machine segmented region of interest. So what is the intensity based similarity measurement of segmentation? So for the binary images, that is, as the segmentation output is always given as a black and white, so pixel oriented simple matching coefficient based similarity measurement in between the ground truth and the segmented output is the popular method for performance evaluation. So the high bill of disparity between segmented output and the ground truth indicates more error in the automatically segmented image, which in turn signifies lower performance of the segmentation algorithm. Suppose in case of the figure 12, we see that the red boundary area belongs to the ground truth and the blue boundary area represents the segmented output that is generated from the machine level algorithms, that is UNet or SegNet. So basically true positive is basically the intersection of the S object divided intersection of the S object towards the